Hey friends, so in this video we'll be looking at this question trigraph from SPOJ. Okay, so let's quickly go through the summary of the question. So it says that this is the starting point. Okay, so this is the starting point. Number of columns will always be 3. Okay, and number of rows will be greater than equals to 2. This is the initial point and this is the final point. You have to reach from initial point to final point. And so even if the size of the graph increases, so let's suppose we add a new node here and we add a new node here, the edges are going to remain as is. So we can safely assume that all the edges are just the replica of so basically new rows are just the replicas of old rows, but these values can be changed. So this will be 20, this can be 25, this can be 0 or something like that. Okay, so number of rows can be different, more than 2, but number of columns are limited to 3. Okay, fine. So what we have to do is we have to travel from initial destination to final destination, and we have to travel in a way such that our cost is minimized. So let's suppose I'll take an example. So let's suppose I travel for 7 to 7. So the cost here is 14 to this 14. So the cost becomes 28 to this 15. So the cost is 28. This is 7 and 37. And then I reach here. So this becomes 43. The other way to reach to this point is 13 plus 7, so this is 20 plus 3, 23 and 29. So we see that 29 is smaller than 43. So this path, the other path that we have taken, so this path here is much more optimal than the other path that we took here. Okay, so the question says that given a graph setup like the one shown in figure, so this is the figure. You have to find out the minimum cost from reaching the initial point, that is this point, to final point, that is this point. Okay, cool. So let's start solving this problem. Okay, so now there are two solutions to it that immediately comes to my mind. One is a recursive solution. Okay, what does it mean? So it means we travel from 7 to 5, we travel from 7 to 13, we travel from 13 to 3, we travel from 13 to 6. Then we recurse back to 3. Let's suppose from 3 we travel to 12, from 12 we travel to 6, from 12 we travel to 16, and we travel to this. So essentially this means, what this means is that you are traveling every single node. So you are basically trying to figure out every single path which is possible to reach this node 6. However, this is not a very optimal solution. This will be an exponential complexity solution. So definitely, if I mean, this is not even a practical answer to this question, but if you are solving this in a competitive programming environment, you have to be very careful of the time. So and time is limited to 0.262 seconds. So recursive solution is not going to work for us. Okay, then what's going to work for us? Let us see. Okay, so I would, for the time being, I would assume that this whole thing is not there. Okay, so the graph starts from this place. What and so this 13 here, this becomes the initial position. What does change in the, what how does this impact the graph? Does it change the question? No. Does it change the let's suppose the structure of the whole problem statement? No, everything remains same, which means if if we solve for if we can if we are able to solve for this subgraph, okay, the optimal solution to this subgraph is also going to be helping us to get the optimal solution if we had this first row in place. Okay, now suppose these two rows are not there. How are things going to change? So everything is going to remain same, but so this is going to be the initial point. Everything else will remain same, and the optimal solution for this graph here is going to help the optimal solution if we add the second row, and this addition of second row is going to help for the optimal solution if we are going to add this row. So why is this actually happening? Let us see that part. So the point that I'm trying to make here is, if had this just been the graph, if we had taken a non-optimal solution, so let's suppose its starting point is 3 and we reach 6 by going through this direction. Okay, so this is not possible. So let me quickly erase it. Okay, so this is not possible. So we go to 6 using this direction. Let's suppose 3 to 15 to 6. Okay, now for this, now that we have solved for this this small subgraph, okay, then our problem, if we now add this another row here, our problem becomes, so the initial point is 13 and our problem now is to reach 6 again. Okay, and we have solved for this 3 here. However, the answer to this 3 is non-optimal. So whenever we try to query 3 from 13, so if we are trying to query what is the okay, so uh, if you are going in a reverse direction, so from we reach 3 from 6 in a cost of, so 15, 6, 21, 22, 23, 24. So 13 if we query, so this node 3 is going to answer 13 plus 24, okay, which is not optimal. So the answer traversal, so the solution traversal from subgraph to another graph, another row, is not correct. Okay, so this means every subgraph is actually a simple, I would say that this has got optimal substructure, which means the sub problems to this whole bigger problem is actually contributing to the optimal solution of this bigger problem. So if we figure out the non-optimal solution to a sub problem, it will actually give us bad results for our original problem. Okay, so now this part is clear. Let's move to another part. So this is the first observation. Actually, this is an observation that I mean we can make just by looking at the graph. Okay, is that it is following an optimal substructure. Second is, now this 13 here. 13 can be reached via 7, via this 7, via this 5, and via this 13. So had we been solving this question using recursive solution, we would have reached 13 for 1, 2, 3, 4 times. Okay, which means that, and now let's suppose we have solution to 13. Okay, and we are reaching 13 from 4 points, which means we are querying this 13 again and again, which means this also has overlapping subproblem. This 13 appears, this 13 can come into the path from 4 different directions, and thus had we been solving it using recursive solution, we would have solved for 13 for 4 different times, which means this 13, or maybe this node 7, this 6, this 12, any node in this whole graph is actually contributing to overlapping subproblem. Okay, now that this question, so the whole structure of this question is showing these two properties of optimal substructure and overlapping subproblem, we can confidently say that we can solve it using DP. Okay, fine. Now that this part is clear, that we can solve it using DP, and the original recursive solution wasn't very correct. Let us try to make a solution out of the whole concept of DP. Okay, how do we do it? Okay, so let's think of it this way. We have to reach the final point 6 here, and this is our initial point. Okay, So what is the, okay, I'll remove this also, and I'll remove this also. What is the minimum point to reach this minimum cost to reach this 7? It is going to be 7, because we are taking the cost of current node also. What is the minimum cost to reach this node 5 here? It is going to be 12, because the only way to reach 5 is via 7. There is no other path to 5. Okay, now see this. What is the cost to reach this node? Now we are talking about this node. I will take a different color. Yeah, so we are talking about this node here, the 7th node. What is the cost to reach this node from this direction? This is 7. What is the cost to reach this 7 node from 13? This is 13, and there are no other paths. So what is the most optimal way in which you can reach 7? Answer is, answer is minimum of these guys, which is 7. Similarly, what is the, now we are talking about this other node here, so let's make it brown, light brown. Now we are talking about this guy here, 13. What is the minimum cost? I'll write the solution here. So what is the cost of reaching this 13 from 13? It is 13. What is the cost of, minimum cost of reaching this? Okay, in fact we can actually ignore this this whole thing here, because we are never going to reach to this node 13, because we are starting from 7. Okay, so I will actually remove this component here. Yeah, so minimum of, so what is the minimum cost to reach 13 from 7? It's 7. What is the minimum cost to reach this 13 from 5? This is 12 plus, okay, so this is minimum of, I will say, okay, 12. And what other ways? So you can reach only in two ways. So this is n plus 13. So it is 7 plus 13 equals to 20. Let us see this particular node here. I'll choose a different color. Let's choose this color. What is the minimum cost to reach this particular node? This is minimum of, again, 7. Then you have this 12. And then you reach via 13, which is 20. Okay, and there are no other ways to reach this. Plus 6 equals to 7 plus 6, which is 6, 6, 12 and 13. Okay, so in this fashion we are able to actually deduce that the minimum cost, to reach 7 is 7. This is 13 is 20. Okay, I'll write it properly. uh, this place is 20 and this is 30. Okay, I'll remove all other things, so that it becomes a little more clear, the whole diagram. Okay, so now we'll use the same concept for third row of the problem. Okay, now we have these data intact with us. Okay, and let us start looking into the third row. What is the minimum cost of reaching this 14? This is minimum of, so this is 7 plus 7, which is 14 actually, not 7. We have to add the cost of the current node. So this is 14 comma, similarly 20 comma, and then you can reach only via two ways. So plus 14, which is 14 plus 14 equals to 28. So the answer to this place will be 28. Now let us talk about this other node in the center. This is, this can be reached from three places. So this is 14, so minimum of 14 comma, this was 28. Okay, so 20, oh, okay, sorry, let me write it properly. So this is 14 comma 28, and this can be reached from the center node 13 also. So this is 20 comma, and it can be reached from 6 also. So this is 13. So 13 is giving us the minimum value. So this will become 13 plus 3, which is 16. Okay, so this will become 16. Let's take a different color and let's solve for this 12 here. So this is minimum of 20 comma and 16. So 16 comma 13 at the top. So 13 is minimum. 13 plus 12 equals to 25. So this is 25, 16, and this is 28. Okay. Now let us see what is the minimum to reach this place, this 6 here. Um, okay, before that, let's solve for 15. So 15 can be reached in minimum of 28, comma. Uh, so we have reached, so we can reach this 15 from the center node also, which is 16. Then 16 plus 15 equals to 6, 5, 11, and 31 here. So to reach this node 6, we have minimum of 31 that is coming from this direction, and then 28, 28, and then 16, which is coming from this direction, and the final guy is here 25 equals to equals to 16, and plus adding this another cost of 6 equals to this is what 1222. Okay, so this is 22, which is not as per the answer to this question. Okay, and the reason is we might have missed something for sure. So this is 7, 6, 13. 13 plus 3 is 16, and 16, so 7, 20, 23, and 6. So this is what? This was 7 plus 6, 13. 13 plus 3 is 16, and 16 plus 6 is 22. Is there something wrong that we are doing? So this is 7. The cost here is 13. So 7 plus 13. So we have reached till this point 16. I'm missing something. So this is 7. Okay, so this is the cost till here is 20. The cost to this point is 7 plus 6, 13. And so there's a mistake that I did here. So the mistake is this. The mistake is this is 14. 14 plus 3 is 17. The total cost is 20. 20 plus 3 is 23 here. Okay, and 13, 16. Let me just clear the board once. So let's see this. This is 7 plus 6, which is 6, 13, 16, and 6, 22. This is 20, 23, and 29. So there is something wrong that we are, unlike the cost of the trigraphs are associated with vertices rather than edges. Okay, which is fine. So this is 20, 23, 29. 7, 6 is 13. 7 plus 13 plus 3 plus 6. 7 plus 6 is 6 is 13. 13 plus 3 is 16. And 16 plus 6 is 22. Okay, let us scroll down and see if this actually is the answer. Oh, okay, so I was, so 22 is the right answer. So whatever we figured out as the answer is correct actually. Okay, so yeah, so this is how it works. So we have seen how we tried to, the approach that we followed was for each node we'll find out the minimum cost to reach that node, and the way to find out that minimum cost is that you consider all the edges. Okay, you consider all the edges. So there are two edges in this case. In the corner case there are two edges only. You consider all the edges which are adding to, which can probably add to the cost of that particular node, and you take the minimum of it, and add this whole thing here. So we'll quickly, so this is the approach to solve this question. Okay, I will now go ahead and write the code to solve this question. I'll be writing this code in Python. Okay, the concept is very similar to so the algorithm will remain same for Objective C as well, and the whole solution is actually very simple. So it shouldn't be difficult to understand the Python code. Let us quickly start writing the solution. And before we write, we'll just have a look here. So this is the first line is the number of inputs followed by so the not the number of input, the number of rows, and then we have the graph set up here. We know how the graphs are related, okay, and then a zero indicates end of test cases, okay, and then this is the way in which we have to print out the output. Let us start. So I'll quickly save this. So text documents video, we go to SPOJ, new folder, okay, this is the name, create and save. Okay, let's start solving this question. So while true, because we do not know, I didn't save this file actually, so file save as, in this video we'll write it .py. Yeah, so while true, because we do not have a number of test cases at this start, okay, number of rows, let us take this as input. So this raw underscore input will help us get the string value into input, and then we are casting it to integer. Okay, if number of, so there are no brackets here, if number of rows equals to 0, we break our algorithm. Okay, now this is where we start solving it. So we make a grid, okay, and we initialize the grid to have none values. Okay, so this is just the initialization part of the grid, um, and for y in range of 2. Yeah, this is looking fine. Okay, this is looking fine. So what is this? So this grid looks something like this. So this is, let's say, none, none, none. Okay, comma, uh, and then I'll again, so none, none, none. So I have taken a grid of basically a number of rows are 2 and number of columns are 3. 2 into 3 size grid is what I have made. I'll come to this point, why did we actually made this grid. Okay, this is a very interesting part of solving this question. Okay, I'll come to this part again. Okay, let us create this input array, which is map of int comma raw input dot split. Okay, so what we are doing is we are basically just taking the raw input, we are splitting it on the default delimiter of space, and then we are mapping, and then we are mapping everything to an integer, and this is an array that gets prepared for us. Okay, okay, so let us move again. This is how we do it. So grid of 0 comma 0 equals to, let's take a very big value, okay, so that it does not impact our code, and the grid of 0.0 is this 13 here, this one here. Okay, so we actually do not have to care for that particular value. The reason why we are taking this as a very big number is because when you move from 13 to 7, when our algorithm checks this 13 to 7, this 13 should give actually a very big cost to us, so that it does not impact the solution when we take it from other when we take our minimum values from other nodes, other incoming nodes. So each value is less than, say, so 1 2 3 4 5 6 zeros, and we have got 1 1 2 3 4, more than 6 actually, so we are very much safe. I'll reduce a bit, so 1 2 3 4 5 6 7 8, this is also fine. Okay, this is okay. Now let us take the value of grid 0 comma 1 equals to input and this array of 1, okay, and grid under 0 comma 2 equals to input array 1 plus input array 2. So what have we done till now? I'll tell you. So if our grid was looking something like this, so this is how the entire setup was done. Okay, just a moment. Yeah, so this is how the entire setup was done. So this is the first row, okay, this is the second row, and this is the third row, and this is the fourth row, and this is how it goes. It goes from here to here. I'll quickly make this graph so that it becomes very clear. And 1 second. So yeah, so it goes from here to here, and this is fine, this is fine. 1 2, okay. So and this direction is incorrect here. This is not the direction, it's opposite. So this is how now everything will remain as is. So okay, yeah, and this is our final point, and this is our initial point. So the grid till this point, in the code, we have made grid 0 as this value 0 0, grid 0 comma 1 as this value, and 1 comma 1 as the sum of 0 comma 1 and 1 comma 1, because the only way to reach this point is through this point. There is no other way to reach this point. Okay, now let's go back to writing code again. So till now it is fine. We'll call this row, we'll make a variable called row. I'll call it as r, as 1. So this is 1 because we actually start dealing into our algorithm from this row number 1. Okay, so let us move to the next line of the code. For I in range, so this is the normal for loop, 0 comma number of rows minus 1. Okay, input array equals to map. Now we are again so at this point of time, so when we were here, this place, we read the first line, which was 1375. So we read the first line, which was 13 comma 7 comma 5. Now in for loop here, we'll read each line, okay, and read each line and process them. So we are going in top down direction in this graph. Okay, let us see this now. So again, the line will remain same as above line. I'll copy this from here. So we have got our input array. Now we'll make a variable underscore r equals to r, and this is, I'll tell you what happens here. So this symbol is called bitwise exclusive OR in Python. Okay, what happens is if the value of the second component in this symbol is 0, the output remains as R. However, if this value is 1, the output gets the complemented value of R. So if 1 is 0, the output will be 1. And sorry, if R is 0, the output will be 1. And if R is 1, the output will be 0. So why are we doing this actually? Now, there comes the interesting point of making this grid actually 2 comma 3 thing. So the point here is, when we have processed this node here, okay, when we have processed this first row here, when we have processed this first row, this means that we have solved for this first row in optimal way. There is no there is no edge which is coming from let's say a row plus 1, which is second row, or row plus 2, row plus in. So the edges are coming from top to bottom direction. There are no edges from bottom to up direction, which means if we have processed a row 1, we have processed it optimally and we do not need the rows above it. Okay, so at any given point of time we'll be needing only two rows. One is the one is the current node that we are at. So the current node initially was 0, and so previous node, actually not current node. One is the current node that we need, and second is the previous node, from which we evaluated the current node. Okay, and then when we go here, we so this is on 0th row. This will be on first row of the grid. This again we will populate on 0th row, and when we now, so this 0th row will be populated based on this first row, and again we will populate the first row of grid using the 0th row of the grid. So we are we are reusing um, the two rows of our grid matrix that we have made to eventually come out to the solution. This is very important for us because this is saving some space for us. Okay, so we didn't actually need to create a matrix which is of size equals to the number of rows in this graph. Okay, so this is how we get using underscore is how we get the ability. So using this complementary bitwise exclusive OR is how we get the ability to use a matrix of two rows to solve a graph of n rows actually. Okay, I hope I'm clear with these concepts. Okay, let's see how it works now. So grid of r comma 0. Now r is 1 here, so we are solving a first row equals to input array of 0 plus minimum of so we can come to this place from two nodes. Okay, so underscore r is the opposite of r, so r here is 1 and underscore r is 0, so we are referring to first row here now. Okay, um, underscore r and 0 comma grid underscore r comma 1. So only so you can reach this place here, um, this place from only two rows here, two nodes. So we just have two comparisons here. Okay, so this is fine. Let's see what happens with grid number with this node here. Okay, uh, yeah, so r comma 1 actually, so equals to input array of 1. We are adding the cost of this current node plus minimum of, now you will be able to come to this node, so which is, so we are talking about let me take this white color. So we are talking about this node. You are able to come to this node from 1, 2, 3 and 4 places. Okay, so we have to consider all the 4 values when we take the minimum. So this is grid of r comma grid of r comma 0 and r comma 1 will remain as is, and we will also have, so minimum can only take 2 values, so I'll compare these two, comma I'll compare the other two guys, which is grid of underscore r comma 1. Okay, so this is actually, this will be r here. Okay, and underscore 1 comma grid of underscore r comma 2. Okay, and we'll take a global minimum, so that we have minimum from all these guys. Now let us look at what happens with the third column here. So r comma 2 equals to input of input array second element plus minimum of, and we can reach this third column node from only 3 places. Okay, so this is minimum of, and I'll take this as grid underscore r comma 1 comma grid r comma r2. So we have got two values comma, so this is one minimum that we have got, and then finally we have got underscore r comma 2. Okay, so wherever we are using underscore, we are referring to the previous row, and whenever we are using this r, we are referring to this current row. If so, I kind of understand that there is a lot going in the code and the diagram. If you find it confusing, I would recommend you to pause this video, look at all the equations that I have written here, okay, and then just try to solve this question. Okay, this should be 1 and not 2, so this is looking fine. Underscore 1 underscore 1, yeah, this is fine, and then we can reach from 2 also, so this is also fine. And at end we do r equals to underscore r, so that next time if r was 1, we are simply making it 0, and if r was 0, we are simply making it 1. Now when this is done, we write, okay, so we have to do one more thing. We have to keep a count of the test cases. So initial count is 1. Okay, so this is how we write. So count plus dot star, we are just formatting the output. This is string grid of uh, number of rows minus 1, because our index is starting from 0, and 1 and 1. Okay, now what this 1 is, so I'll tell you. If okay, so see this here, this is 0, this is 1, this is 2, this is 3. Okay, now what's happening is, this was r equals to 0, r equals to 1, r equals to 0, r equals to 1. So you would observe that all the odd ones, all the odd ending rows will have r equals to 1. Okay, and all the even ones are having r equals to 0. So if number of rows in the question is given as 4, number of rows minus 1 will become 3, equals to 3. Okay, and number of rows minus 1 would actually become 3, and now we are seeing this number of rows minus 1, which is 3, and so this 3, just a second, what's happening here, I wrote something incorrect here. Let me just see. So this is how it should be, grid number of rows minus 1. Okay, this is how it should be. First of all, um, number of rows minus 1, uh, yes, grid of, let's, number of rows minus 1, yeah, and we are doing an and over it, so we are doing and and over it. So this is so this equation here, right? So this equation here help us get either a 0 or a 1, based on how our based on the number of rows. So if it is, let's say, the number of rows of 4, we'll get a r equals to 1 here. Okay, which means we are querying grid of 1 comma 1. However, if the ending row is 3, so it becomes 2, and we'll get it as grid of 0 comma 1. So this is how we use this number of rows to uh, actually properly query our grid. Okay, now let us move to next line of the solution, which is just to increase the count. So if I increase the count to plus equals to 1, everything looks fine. Let us run this question in Python. So documents, videos, video, ls, SPOJ, ls, cd. So this is AC, and yeah, so Python AC dot py. Okay, so there is a problem in this line. Let us see. It says none for x, invalid syntax. None for x in range. It should be in is missing here. In range. Let us run this again. Count plus equals to 1. This again is an invalid syntax. So a simple solution to this is just to make count equals to uh, count plus 1. Okay, let's see now. This again is invalid syntax, and this, why is this invalid syntax? Because so this is closed, this is not closed here. Okay, uh, yeah, this is looking better now. Let's take our test case. So let sh command not found, and this also says that int to none type is not supported, and this is giving an error in minimum of these guys here. So what we can probably do is we can we can actually initialize this with a very big value. Okay, and let's see. So 4 13 7 5 7 13 6 14 3 12 15 6 comma 16. So the output is, it says, is 16. Okay, which means there's something which is not right with our code. Let us quickly go through the code once again and see what's not right. So these are okay. This is underscore 0 underscore 1. This is also fine. This is underscore 0 underscore r comma 0 is compared with r comma, this should be 0, actually this shouldn't be 1. Okay, so underscore r comma 1 and underscore r comma 2 is fine. Underscore r comma 1 it gets compared with r comma 1 and underscore r comma 2. Okay, let's now run this code again. So 4 13 7 5 7 13 6 14 3 12 15 6 16. Now this output is fine. Okay, I'll go ahead and submit this solution to SPOJ to see if everything is working fine or not. Okay, so we'll select our language first. So this is 2.7.3, submit, and this shows time limit exceeded. Okay, let us see why would it do that. Um, if number of rows equals to 0, we break. This is not needed. For I in number of rows, print string count plus 1. This is looking okay, there shouldn't be any problem to it, and we are just printing it here, and we have a for loop in this range 0 to number of rows minus 1. We are reading the input, so this is actually looking okay. I don't see a serious problem here. What was the problem when it said? Okay, so let me make it run none and submit it again. Let's see if that's what causing it a problem. No, that is not causing a problem to this code. Okay, where else can we improve? So we read input array, int draw input split. This is all fine. This is all fine, and we're just having a loop over it, and we are having few minimum checks. So what probably could be going wrong? And then we are just printing the output and increasing the count to 1. This is looking okay to me. Oops. 0.262 seconds. Okay, let me just check. I mean, let us see how what could be the probable problem. So everything is okay, and this shouldn't take too much of time. What is 0.262 seconds, right? So it may be a few things here and there that is impacting our code. Let me just try submitting it once again. I'll also look at everything properly. Okay, so uh, let us see. So have we done anything that is not needed? We'll make it none here. Okay, and we'll also 1 2 3 4 6. So this is okay. Input array 1 plus 2 is okay. Count is 1, number of rows equals to 0, then break. Okay, this is fine. Input array we have taken, we have split it. R equals to 1, number of rows minus 1, and then we are mapping this to input array again. This is fine. Input array of 0 1 2, and we are doing few minimums. So one thing that we can probably do is, so the one thing that we can probably do is, I think this should just pass. Let me just check it once more. If it doesn't work, we will stop writing print statement again and again. And okay, so this works fine actually. So it works only on the edge. So it is 0.26 seconds, and the limitation was 0.262 seconds. Okay, so yeah, it actually worked fine. But okay, so one of the reasons that people do not use Python in programming context is because the language is inherently so. It's an interpreted language. So any variable or anything that you write there, right? So you don't really know what this number of rows are or what this count is until you go ahead and run the program. So only when you run the program, you get to know that at runtime that this variable is actually behaving as an integer and not as a string or let's say a character or something. So if you, I would recommend you to solve this question using the same algorithm in C++, okay, and try seeing the time difference between Python and C++, okay. I'll go ahead and do one more thing. While I publish this solution on GitHub, I'll also publish a solution written in C++ and with just a time comparison at the top of both the files. Okay, this was a very lengthy video and there were few hiccups in the video wherein we were not able to so initially when I started explaining the video, uh, there was problem in having this test case run properly because I was assuming 29 is the solution, and then we had few time limit exceeded in the end. I apologize for them. I'll be better prepared for my next videos. Okay. Dynamic programming is inherently a bit complex than other data structures, but I'll try to be better prepared for my next video. I hope you would have enjoyed watching. It would have been an interactive session. There were lots of mistakes. Okay, if you um, if you find this video helpful for you, please go ahead and like this video and share this video. Subscribe to my channel for further updates on algorithmic questions. Thank you so much for your time.